Here we'll see how the wall resistance through a pipe is going to be analogous to a resistor in an electrical circuit. So we'll see our pipe. And then we have our bit of fluid passing through it. So we're going to say that we're looking at a length of L of our fluid in this pipe, and that the pipe is going to have a diameter of, I'll call it capital D. Now I'll note that this derivation for the wall resistance and what we're going to find as the equivalent resistance is going to be good only for circular pipes and only good for laminar flow, as we'll see it when we start to apply these equations. If we have a non-circular pipe, we're going to have a different relationship, and if you were to have turbulent flow, again, you would have a different relationship for what the equivalent resistance is going to be. So where we can start here is with the Darcy equation from fluid dynamics. So that is going to tell us about the major head loss. So I'll call it H sub L major. And drawing back from fluid dynamics, you might remember this. It's going to be this constant F times L over D times velocity squared over 2 times G. Next, that tells us about the major head loss as we go through our pipe in this case. So what are some of these things? Let's look at the F first. So the F, that is the Moody friction factor. And it has, well, two possibilities. Either it's going to be 64 over Reynolds number, and that is going to be the case if we have flow that is laminar. And if we have flow that's turbulent, then it's a different calculation. In that case, we are going to have to look it up in the Moody chart. And it's going to be dependent on different factors. So the Moody chart would give you the F if it was turbulent. The one we are interested, though, in is for the laminar flow. Again, that's why this derivation will only be good for pipes with laminar flow in them. It's going to be more complicated if the flow were to be turbulent. So that is the value that we can put in for F is 64 over Reynolds number. So I'll rewrite this over 2G. All right, what we also need to recall from fluid flow is how did we calculate Reynolds number? Now the Reynolds number for a circular pipe, which is what we are dealing with, is going to be the fluid density times the velocity times the diameter. Again, this is for circular pipes, over the dynamic viscosity, that mu value. And partially what the Reynolds number is going to tell us is, do we have laminar flow or do we have turbulent flow? So the rule of thumb that we use is that if our Reynolds number is less than 2000, then we have laminar flow. And again, since we are using this Moody friction factor F of 64 over Reynolds, we have already assumed laminar flow. So we might need to check this if we have a case where we're not sure, is the flow going to be laminar or not? Well, first, let's calculate the Reynolds number, make sure it is laminar, then we can go and calculate our equivalent resistance based on that laminar flow. So if it's less than 2000, it's laminar. Again, that's going to be the limitation or the assumption we are making for this derivation. And also recall, if it's greater than 4000, then we usually call that turbulent. And if it's in between, then we are somewhere in between this transition between laminar and turbulent flow. But we're sticking with less than 2000 for this particular derivation. So we can do another substitution here back into this Darcy equation for major head loss. So it's 64 over Reynolds number, as Reynolds number is defined over here. So that's the rho VD over mu. So 64 over Reynolds number, I can rewrite that as 64 mu over rho V times D times the L over D times that V squared over 2G. I can do some simplification here. So for example, I have a v in the denominator and I have a v squared up top, so that will go to just v. I have this d, so that will become a d squared when I combine them. And I have this 2 and this 64, which will become 32. So let me write this a little bit cleaned up. 32 mu L times V over rho G d squared. So where are we trying to go? Remember, the goal is going to be, we really want the relationship between the pressure and the volumetric flow rate, because that's going to be analogous to the voltage drop and the current in the electrical system. So far we have neither volumetric flow rate nor pressure, but it is going to be coming as I keep manipulating this. So I start to have some of the pieces here. I have a velocity. We know that volumetric flow rate is going to be the cross-sectional area times velocity. So what I'm going to do is I'm going to multiply. I don't have an area in here yet, but I want to multiply by the area, the cross-sectional area. But if I multiply in the numerator, I also have to divide by that same amount for the denominator. But the cross-sectional area I can also write as pi over 4 d squared. So I am multiplying top and bottom by 1, because the bottom is the cross-sectional area, but I'm writing as pi over 4 d squared, and the top I'm just writing as a. Again, why am I interested in doing this? Because now I have a v times an a, and we know that that is volumetric flow rate q. So I can rewrite this again. If I combine the 32 and that 1 over 4 in the denominator, I'm going to get 128. I have a mu, I have an L. The V and the A are going to combine into Q. I have a rho, I have a G, I have a pi, I'll bring that out front, and I have a D to the 4th power. And that is, again, just re-expressing this Darcy equation for the head loss. Now, I also know that the change in pressure is going to come from this head loss. So the change in pressure, I'll call it still delta P for now and then drop the delta, is going to be rho times G times the major head loss. So what does that equate to? Well, I have rho, I have G, and now I can substitute in what I have for the head loss in this circular pipe with a laminar flow. I have the 128 mu times L, pi, rho G on the bottom. You can see there's going to be cancellation, times the Q. Rho G and a rho G, that's going to cancel out. So this is going to just be the 128 mu L over rho pi d to the 4th times Q. I'm going to drop that delta because we know we're talking about the change in pressure technically, and that Q is technically the change in flow, or the change in volumetric flow. So P is 128 mu L over pi d to the 4th times Q. Now we're at the point where I have a P, I have a Q, I am ready to do a Laplace transform. So P goes to fancy P, it's now a function of S. 128 is constant, the dynamic viscosity is constant, the length of the pipe is constant, pi is a constant, and the diameter is not changing, and little q is going to go to capital Q. Now I'm looking for that electrical analog. I have that in the electrical world, V equals Z times I. What does this look like? Well, I have no S terms. This is going to look like, well, Ohm's law, V equals R times I, with no S's. So if I look at what I have going on here, this constant in front of the Q is going to be my equivalent R. So R is 128 mu L over pi d to the 4th. So that is the wall resistance, the equivalent resistance through a length of pipe. And again, the restrictions on this being the equivalent resistance was this was derived for a circular pipe, because that was the specific Reynolds number calculation we used, was circular pipe, and This is for laminar flow only because the Moody friction factor that we used, that 64 over Reynolds number, was coming from laminar flow. So once again, if you have a turbulent flow, this is not the equivalent R to use. If you have a non-circular cross-sectional pipe, this is not the R to use for that. Right, looking at this, the denominator, I have a diameter to the 4th power, similar to what we saw for the inductance or the equivalent inductance for large diameter pipes or large cross-sectional area pipes. When the area was sufficiently large, we can ignore the inertia. The same is going to be true here. As the diameter of the circular pipe gets larger, since we have a d to the 4th on the bottom, as d increases, the resistance is going to decrease. So diameter goes up, resistance goes down. So for quote unquote large diameter pipes, the resistance, the wall resistance, is going to be negligible. So for large scale systems, we're not going to have to worry about modeling the resistance in the pipes themselves, but as that diameter shrinks, we get to smaller scale systems. Now the resistance through the pipes themselves, or the tubing itself, is going to be of concern to us, and we will want to include its resistance when we're making our model, and then that's going to come into play when we are coming up with transfer functions.